Welcome to this video on bundling conductors. Put them in a raceway and a nipple or bundle them. And how would you determine the ampacity? That's what we want to go through today. But before we get into the presentation, I would like to invite you to become a subscriber to our videos. And if you do, it sure would help us so that we can keep bringing these videos to you. Now, please consider, and now let's get started. But before we do, I hope you have your code book handy. And if you do, let's turn over to page 158. Page 158, and on the right-hand side of the page, you'll pick up 310.15C1, and the title head is More Than 3 Current Carrying Conductors in a raceway or cable or whatever. And notice what it says here. The code reads, the ampacity of each conductor shall be reduced as shown in table 310.15 C as in car 1, where the number of current carrying conductors in a raceway or cable exceeds 3. Then we have to derate according to the percentages that are in table 310.15 C as in car 1. For example, if you have 4 to 6 current carrying conductors, 80%. 7 to 9, 70%. Now, once you pull more than 9 current carrying conductors in a raceway or cable, you have to be able to afford it. You may have to increase the size of those conductors, which would naturally cost you more money. But now notice the thing that gives us a lot of trouble. Let's just read where it says the 24-inch rule. And basically, it states there that where there are conductors or multiple conductor cables, and they are installed in a raceway, and you do not maintain the proper spacing, then you're allowed up to 24 inches, which they call bundling, and you do not have to derate. But once you exceed the 24-inch rule that you see listed, if you count 3 lines up from the bottom of the paragraph, you have your 24 inches listed there. And that 24 inches is bundling. If you get over it in length of conductors or cables, then you must derate if you have more than 3 current carrying conductors. And that's basically what this rule is saying. Now, if you will, turn with me over, for example, in your code book to page 695. Page 695. And then notice in your code book there that if you look at note 4 on the left-hand side of the page, right above the table 2, and it states where conduit or tubing nipples having a maximum length not to exceed 24 inches are installed between boxes, cabinets, or similar enclosures, the nipple shall be permitted to be filled to 60%. And then notice we do not have to derate. We just looked at that in section 310.15C1. You wouldn't have to derate because we have the 24-inch rule there, see, that you see. So you could have it either bundling the cables or conductors, or you could have a nipple as you see there. But the magic word there to me is the 24-inch rule that we would look at. And then you notice if we reviewed our illustration here, which is figure 12-23A from Stallcup's electrical design book, volume 1, notice that we have the nipple there between the service panel and the, say, the auxiliary gutter. And notice you have a 60% fill. Many times people want to know, well, where does that come from if they're not used to using the code book. And if you go to page 696 in your code book, And since that's a EMT nipple, let's just start at the top, table 4. And let's just review the last column to the right of the table. And it says total area 100%. Now, if you're going to have a 60% nipple, just slide over to the 60% rule to the left. And let's say if you had a 1 inch, you could slide down. And that would be 0.519 for that 60%. And if it was in a raceway, you only get 40%. We'll look at that while we're here. So go look at the over 2 conductors 40% fill. That comes from our table 1 to chapter 9. They're on page 695. And notice if you look at that 1 inch, then it is 0.346. You don't have as much room because you have to breathe and get rid of the heat. And notice in that nipple, you're only 2 foot long, so you have each end of it to dissipate heat. So this is another one of the reasons that we can fill it. But now we've just kind of looked at the quick calc below. We've looked at our table 4. We've looked at, say, a 1 inch or 1.5 inches nipple there. But we looked at a 1 inch just to kind of see what it would be. But you could look at the 1.5 inches there and look at your 60% fill and drop down to that 6.5, then you could see that you could fill it just like it says there. You could fill it to that 1.221 that you see in the quick calc. So basically, you know, this rule's allowing you to put more conductors in that nipple because they're only 2 foot long and you have dissipation at each end of that nipple for heat to escape. And then you also have the metal of the EMT that absorbs heat. So that's basically now using a nipple. And then we looked at, back there on page 195, we looked at were more than 3 current conductors in a raceway. We were referred over to our table. Now, let's just go over and take a look at that table on page 160. If you have your handbook handy, go over to page 160 and look at table 310.15C1. And that's where I previously said if you had 4 to 6 current carrying conductors in your raceway, 80%. You see that in the table? 4 to 6, 80%. 7 to 9, 70%. Now, that's using the table. But notice once you put that 10th conductor and pull 10 current carrying conductors through the raceway, you're automatically reducing the ampacity 50% that we will review and look at. But right now, we want to look at our next video, which shows sizing this nipple that you see here in this figure 23-1A from Stallcup's Electrical Design Book, Volume 1. Now let's look at this figure 1223B, and we'll calculate and size that nipple in the previous illustration. Now notice our problem here, we have a question. What size EMT nipple is required to enclose 9 number 12s, 9 number 14s, and 12 number 10s, and 14 number 8, THHN copper conductors? Now, the step 1, we would go to our table 5 to chapter 9. And you would select from the table number 12 wire, THHN. You'd pick up in the last column 0.0133 square inch. Number 14 be 0.0097 square inch. Number 10 would be 0.211 square inch. Number 8 would be 0.366 square inch. Now, we perform the math in step 2. And of course, now we're looking at table 5, chapter 9 still. We're taking that cross-sectional area of number 12. We had 9 of them. Do the math, 0.1197 square inch. The next conductor we have is number 14, 0.0097 square inch area times 9. and we come up with 0.0873 square inch. Now we'll pick up the number 10 at 0.0211 square inch times 12. We come up with 0.2532. Then finally we take the number 8 at 0.0366 square inch area times 14, and when we perform the math, we come up with 0.5124. When we add all of those square inch areas together, we come up with 0.9726 square inch area. Now we would go to our table 4, chapter 9, and we would get 100% fill for an inch and a half that we looked at, and it would be 2.036 square inch area. It's that last column in your table 4 in chapter 9 for EMT. And then step 4, we take the square inch area with a 60% fill, and we come up with 1.2216 square inch area. So again, we would still reference note 4 to chapter 9. That's on page approximately 696. And we would find then that 1.2216 square inch area is greater for that inch and a half, and it would house the 0.9726 square inch area. So it would be an inch and a half nipple that we would use between that service panel and that auxiliary gutter. And then notice we wouldn't have to derate for that total number of conductors because it wasn't over a 2-foot nipple. And you get the benefit with the appropriate connectors being used. They support the 2-foot. So you get a 2-foot support with the connectors, but you also get a 60% fill instead of 40% fill like a Raceway when you're over 2 foot. And you get the benefit that you don't have to derate per table 310.15C1. So that is what this figure 12-23B is illustrating, is sizing a nipple using the values of note 4 to tables chapter 9. Now let's look at this figure 12-22A. That comes from Stallcup's Electrical Design book, volume 1. And we're going to size a Raceway. Now you're a Raceway when you're over 2 foot long. If you're 2 foot or less in length, then you're considered a nipple. And you got that 60% fill that we looked at. But now we're looking at this Raceway over 2 foot long, and then you have to support it, accordingly to the code. Basically, you support within 3 foot of a box, every 10 foot and so forth is a basic support rule for this EMT. If you go to the code and look it up, I believe that's in dot 30 to the section that deals with EMT. See? Now, notice in the illustration of Raceway, you have a 40% fill. You see that? Now, we want to go over to page 696 of your code book, if you have it handy. And then notice when you look at your code book, we have a 1 inch EMT there. And notice if you look at the code book, right-hand side of the table 4 EMT, notice that's a 0.864 that you see at the in the quick calc there, 0.864. That's 100% fill. But we're going to have a 40% fill because we're Raceway and not a nipple. So when you slide over and look at that, that's 0.346. When you multiply by 40%, the 0.864 that we would get there. Now you see that right there. If you're a Raceway, then you see that's where the 0.3456 comes from. But if it's a nipple, 0.5184 that you would get. See, you see the difference? And then notice if you have 4 or more current carrying conductors in the Raceway, you have to derate, and you don't have to derate at all if it's a nipple. But typically, the authority having jurisdiction if you had 25 inches, they could turn you down if they wanted to. It's always a good policy to make sure you're 24 inches or less, and if you can make it less than that, so there's no, there's just no discrepancy there at all. You're going to be in good shape. Now notice in this Raceway, as you see in the illustration, we have 12 number 14s, 4 number 12s, and 4 number 10 AWG, THWN copper conductors. And then notice that we have a 40% fill. Now, we're going to take this 40% fill and we're not going to fill it past 0.3456. And we will do that in our next illustration, which is it's 12.22B as in boy, coming up next. Now let's take a look at this figure 12-22B from Stallcup's Electrical Design Book, Volume 1, and we're going to calculate the size of that Raceway. So the problem, we have a question. What size EMT is required to enclose 12 number 14s, 4 number 12s, 4 number 10 AWG, THWN copper conductors? Now step 1, we're just picking up that cross-sectional area. So once I'm going to kind of let you do this on your own. Go over to Table 5, Chapter 9, and pick up the that table. And number 14 is 0.0097. Number 12 is 0.0133. And number 10 is 0.0211 square inch area. Now that's the square inch area of our conductors that Raceway system EMT is enclosing there on page 696 of your code book. Now step 2, we take the cross-sectional area of that number 14 times 12 of them, and we come up with a total of 0.1164 for that calculation. The next calculation is 0.0133 times 4 of those number 12s, and we come up with 0.0532. The next calculation for the number 10 is 0.0211 times 4, and we come up with 0.0844 square inch area. Now, total of those square inch areas, we come up with 0.254. Now, selecting the size EMT, we go to Table 4, Chapter 9, and 0.254 square inch area requires 0.346. Does 3.46 now, will that house the 0.254? And of course the answer is yes. So in the solution, that 1 inch EMT is required to house that number of conductors, and you have a little bit of a square inch area left if you needed to pull maybe some in later. But now notice we're using Table 5 and Table 4 in the back of the NEC, so you're kind of looking at page 695 and page 696, I believe. So that's what this figure is illustrating, enclosing the different size conductors in accordance with Table 5 to Chapter 9 and Table 4 to Chapter 9. And that's what this figure is illustrating to the user of the NEC. Now let's take a look at this illustration that comes from Stallcup's Illustrated Code Change book, and kind of believe it or not, it's the 2014 edition when this rule in yellow that you see at the bottom of the note was accepted in the code book. Now, what I like to use this one to illustrate the 4 ways, or maybe we should say 4 methods that you could use to determine the ampacity of conductors. Now, from this table, 310.15B3A, that's the 2014 NEC. This table has been relocated and renumbered in the 2020 NEC edition, and they basically went back to the old numbering of the table, 310.16. But now if you have your code book handy, let's just turn to page 160. And on the left-hand side of the page at the bottom, we pick up our table 310.15C1. And then notice, again, we've already looked at this table, but notice 4 to 6 is 80%, 7 to 9 is 70, and once again, I caution you, you pull 10 conductors that are current carrying, above 9 now, you're 50%. So that means you're going to reduce the ampacity of that conductor 50% based upon the type of insulation and the size of the wire. Now, one thing I want to point out, this was added in, and notice at the very bottom of the table, let's just read the last sentence of that paragraph. And it says here, the count shall not include conductors that are connected to electrical components that cannot be simultaneously energized. And that's what this note is telling you. That, and let's just say in the illustration, if you had conductors that are not simultaneously energized in A and B, then only the group, and you'd say, well, A pulls more current than B, then you'd use A. You'd say, no, B group pulls more than A group, then you'd use B. But notice they cannot be used at the same time. When one group's operating, the other group is not. That's basically the rule. And then notice we can use the table. But now notice applying, and notice in the illustration, you do have table 310.15b3a. And that's not true in the 2020. That table would change to 310.16 as you see there on page 160, left-hand side of the page at the very bottom. We have 4 current carrying conductors in this Raceway. So the table 310.16 now, by 2020 NEC, 80%, we would reduce it 80%. What's important now? Well, what's the insulation? THHN. And remember this, THHN in the 90-degree column or any of that insulation in the 90-degree column does not exist until you derate and reduce that ampacity back to a certain value. So in this case, we're choosing 80% from our table 310.16 there on page 160, left-hand side of the page at the very bottom. So we take step 1, 80%, and step 2, we apply it. We have number 12 conductors there that are good for 30 amps. If we looked at the 30 amp THHN type rating, then we would pick up 30 amps that we could use. So it'd be 80% of 30 amps for number 12 in the 90-degree column. And you see that 75-degree column is 25 amps, and the 60-degree column is 20 amps. But we're able to use that 30 degrees, the 90 degrees, 30 amp rating for derating and reducing the ampacity of the conductor. So 80% of 30 is 24. So that conductor is good for 24 amps. Step 3, we apply the table 310.10 in the 2020 NEC, and 240.4D as in dog stays the same. It hasn't changed. So it'd be 100% of 24 amps now, it'd be 24. But 240.4D says the number 12 wire is only good for 20 amps because it's restricted to a 20 amp overcurrent device unless what? The load appears in table 240.4G, such as an air conditioning load, a motor load, or any of those loads there that would have an inrush characteristic for it to start and accelerate and drive the load in some cases. So we're using the table, and if you have groups of conductors, and you could have 3 groups. You could have A, B, and C group. And which one of those groups pull the most amps, and the other 2 groups were not energized while one of the other groups are working, then, you're home free. You don't have to figure, say, 9 current carrier conductors in there, see, because they're not. And so that is a great help to you. So kind of keep that in mind. And then we're going to look in the next illustration where you can go to the Annex B as in boy, and you have two other methods of loading these conductors, but you'd always want to check with the authority having jurisdiction when you use the Appendix B back there. You'd want to make sure you use that annex according to the authority having jurisdiction and their approval of your design and your installation after you perform the calculations. But, that's what this illustration is illustrating to you. When you have more than 3 current carrying conductors in your raceway, or you have groups, and those groups do not operate simultaneously. Now remember, just as kind of a little recap here, we're going to be looking at our figure 8-16, and it's from Stallcup's Electrical Design Book, Volume 1. But before we get into this third and fourth method of determining the ampacity of conductors based upon conditions of use, let's go back to page 160. And remember here on page 160, looking at our table 310.15C1, that we could use those derating percentages, reducing the ampacity of a conductor back to 60 or 75 degrees C terminal per 110.14 C1 little a or b, depending on voltage. And then, of course, in the last sentence, below the table, we pick up the grouping, where if you had Group A and Group B, say, and Group A pull more current than Group B, but neither one of them would be energized at the same time, then we could just use the Group A, and the Group B would be home free, see. But now we're going to move from that, and I'd like for you to go over to page 158 with me now. On page 158 of your code book, right-hand side of the page, we pick up C, adjustment factors. And C1, we picked up the 24-inch bundling rule. We went over to note 4, to table 1, to chapter 9, there on page 695. We picked up the nipple, 24 inches or less in length, and we kind of looked at that little magic number, 24 inches, where you wouldn't have to derate if you bundle or had conductors pull through a nipple. And it really didn't matter how many conductors or cables that we would have. Now, I would like for you to look at the informational note 1 to C1, and you have C Annex B. Coming right out of the gate of informational note number 1, C Annex B, right there, put page 629, right in, page 629, and let's move to the back of the code book and pick up our table B.211, right-hand side of the page. Now this is loading half of the conductors. If you had, say, 16 conductors, you're loading 8 of them. 8 you're not loading. Now we used to do this all the time. We would run a trunk line of conductors in a large pipe, and then we would branch out at pull boxes and pick up branch circuitry to outlets and things like that. But we would make sure that the current was evenly proportioned on those conductors, so we didn't overload the conductors under a continuous duty where the load could operate for 3 hours or more, as stated in Article 100 for continuous duty. Now, notice here, you can say, well, now if I had 18 conductors, I'd fall in the group of 10 through 24 number of conductors in the table, first column, 70%. And 70% of a number 12, say, 30 amps is 21 amps, you're still a 20 amp conductor, but you're only loading 8 at one time. You understand that? Now you say, well, what if I wanted to load instead of 8, 12 of those conductors? And more than half. Now we'll have to go to page 717. So just back up to page 7-17. And then on the left-hand side, you have your example 1. This is where we're just loading, say, half of your conductors. You see in the square root, the amps of that conductor would be 0.5, which is loading half, 50%, times you had 24 conductors you pull through. You divide that then by 12, because you're loading half of the 24th, take the square root, and you can see if you had a 20 amp number 14 conductor, 90 degree C, that'd be 70%, and you see that you have 14 amps. 240.4B says you can move up to the next size overcurrent device, which would be 15. Now, example, if you wanted to pull more than that, now you have to get the formula to the left, which we're going to do, and you would run it, and then notice in the example 2, you're going to load 18 of those. You're not going to go near my graph, you're just going to load 18. So the amps in would be 0.5, loading 50% of 24 conductors, but you're going to load 18 of them. And then again, times the number 14, 20 amp in the 90 degree C column, THHN, you'd multiply that times 70%, 11.5. That means you could, as long as you did not pull more than 11.5 amps, you're in the chips. And what is the next overcurrent device above 11.5? 15 amp. And that's in accordance with 240.4B of the code. Now what we're going to do here is go through this figure 8-16 from Chapter 8 of Stallcup's Electrical Design Book, Volume 1. Now, let's look. We're applying 50% load diversity here in the table. So we have 16, number 12, THN copper conductors. Now, number 12 is good for 30 amps in the 90 degree column when we look at table 310.16. Just go to the 90 degree column for number 12. Now that 30 amps can be used. In other words, it does not exist. Remember that. Now we apply the table B, 310.14B to 11. 16 conductors at 70% is 21 amp. So we're 20 amp conductor because we're only loading half of those conductors. So out of the 16, we're only loading 8 of them. So the solution says, okay, you're 21 amps as long as you just load 8. So I can use number 12 conductor, put it on a 20 amp device, and I'm in business. See? But now the next one, the question is, what is the allowable ampacity of each conductor when applying the 50% load diversity? And what we're doing, we're just checking to see if the wattage and amps match out. So we, again, table of B310, .14B to 11, and section B.7a. The watts is the current squared times the resistance of a number 12 at 50%. So we just use one as a resistance as long as it's 1,000 foot or less. So we would pick up then and do our 30 amps squared times 1 times 16 times 50%, we come up with 7,200 watt. Now in step 2, we're going to find out how many amps that would be. So we have amps and the watts, number of conductors. So in the square root, we would have the watts equals the amps and take the square root of it, see. So we'd have 7,200 watts divided by 16, take the square root then of that value, 450, and we come up with 20.2, just exactly what we got in the above calculation. All they did was drop the 0.2 in accordance with 220.5b. I believe it is. It says, if you're 0.5, 0.6, 0.7, 0.8, 0.9, you round up. But if you're 0.4, 0.3, 0.2, you round down. So that's what they did. So 21 amps. So now we're applying a derating diversity of the 16 number 12 conductors. But notice we have 16 conductors. And if we go by table 310.16, then it would be 50%, because we have 16 number 12. So in the table 310.16 and then table 310.15 C1 in step 2. Step 1, let's don't get ahead of ourselves. Step 1, we're picking up the ampacity of a number 12 THHN, which is 30 amps. Step 2, we have 16 conductors. At 50%, in accordance with our table 310.15 C1. So 50% of 30, that conductor is only good for 15 amp. Number 14, that's the best it could be. We had to upsize that conductor to number 10, and in the 90-degree column, we'd have 40 amps. Now we take 50% of 40, our conductors is good for number 12 now, see, good for 20 amp. So you'd have to upsize that conductor. So the solution is the 16 conductors is good for 15 amps. Now, instead of loading just half or loading all of them at an expense from table 310.15 C1, there on page 160, left-hand side of the page at the bottom, then notice if we go to the quick calc number 1, then we're applying our tables, B, dot 310, say 14, B211, and section B, dot 7A. And then the current would be the square root of the 50% times the number that we would have there, then times the A1 that we figured. So looking at that, we would have then in the quick calc outline here, we would have our 0.5 there times 16 divided by 16, and that'd be 0.707 times 30 amps, I believe that is. That's a little hard for me to see there. It's either that or 707 times 30 amps, and we come up with 21.2. Now that's exactly what we got up at the top here, isn't it, in our second calculation? Same thing. So we know then that if we load by the quick calc 1, that's what we come up with. But now in quick calc 2, we're going to take and load just 12. We're going to load 12 of them. Not 8, but 12. So in the square root, we're going to have 0.5 times the number, and then divided by E times A1. So we would come in then, and it would be your 0.5 times 16 divided by 12 times the A1 amps. And then A2, you would have 81% times 30 amps times 70%, and your new ampacity would be 17 amps. What's the next size overcurrent device? That would be 20. But if you wanted 15 amps, you could put that on. That'd give you 15 amps, see? And you'd have plenty because you'd have 2 amps to spare. So, but if you wanted a number 12 conductor, you couldn't put more than 17 amps on it now. That'd be the only thing. We used to put on the breaker where we did this kind of thing. And we'd put the amount of amps that you were allowed on each breaker, so an electrician coming in after another electrician would know exactly what the amps of that would be and say, well, what's the problem here? Why can't I put 80% of a continuous load on a 20 amp breaker, or take 125% of the load? So we put the amount of amps, and they'd have to stay within that value either continuous or non-continuous. So the only thing here in the A2 amps, in the quick count 1, I said 0.707, and that's 707. It's just a little hard for me to see that. Excuse me, sir. So that's what our figure 8-16 is illustrating to the user of the NEC.